Sorry for that small problem there. So I hope people on online are able to see the screen on Zoom. Okay, thank you. So the talk is going to be lithium in red giants and implication to stellar models and why lithium. So I'll just talk about some trivia about lithium soon, and then some introduction, and then later on what our group is doing in the last maybe 10 years. So the entire my talk is based on the work done by my students, Vipin Kumar and Raghubar Singh and Deepak and Anohita. They are currently, Anohita is here and then she has posted, and Raghubar is giving a talk later. And then other people, Simon Campbell from University of Monash, David Lambert, Gajendra. So lithium on Earth, some trivia. In nature, lithium, as nature also in the stars, you see in two major isotopes. One is 6 lithium and 7 lithium. And 7 lithium is the major component you see. And much of the global reserves are in somewhere in Chile, and also seawater contains quite a bit of lithium. So, and also lithium is known to be, antidepressant. And but for us, for quite a long time, a lot of theoretical people, as far as observations, astronomers gave quite a bit of headache. In the sense, we didn't know how to see some places very less lithium, some places large amount of lithium. So there are huge reserves. I think Tesla can make 10 billion cars, it seems. This is actually taken from European policy review on lithium because they wanted to see this as a strategic element. I heard that 80% of the lithium reserves on Earth are controlled by China. So now cosmic lithium. So that's for the Earth. So where we produce, much of the lithium comes from a Big Bang. That's called a primordial lithium. And then you can see how this gets produced in the initial period. 3He plus 4He, one of those lithium channel. You get 7 lithium. And then also the 3He plus 4He can go into beryllium, and the beryllium can transform into lithium. Also, the lithium can get destroyed quickly by going back to helium. So that's the Big Bang primordial lithium. What you see, lithium is normally expressed in stars is something like this in logarithmic scale relative to hydrogen. Okay, so what you see here down in logarithmic scale again, the primordial lithium is now actually 2.7 is not observed lithium. There is it's called a cosmic lithium problem. There is a difference between a factor of 4 to 5 between the best estimates from Planck observations and then WMAP observations, and what we have seen in observations in very low mass stars. But I have taken now, because this is a completely new data from Planck and the WMAP, that's a 2.7 primordial. And after we see 3.2, that's never get destroyed, which is basically the ISM value came from Natal cloud. And then what we see in the ISM is something like 3.3, again logarithmic scale. What we see in the sun, it's a much less. Okay, it's a factor of 100 less than what you see in the ISM. Okay, that's again the problem, which we don't know how the lithium got so much destroyed in the sun. So cosmic lithium problem. Okay, I'll just put everything here. See, what we have seen here is lithium is the only one of the elements, apart from hydrogen and helium, produced in the Big Bang. But the other two elements are almost, there is no issue because the observations and theory matches very well. But for the 7 lithium, there is still a problem which is completely unsolved. For example, here, you look at these are the WMAP came from variant density values, which you can produce. So that's a BBM, 2.67, which I rounded off to 2.7. And this is the best observational estimates, that is 2.2. This is called the cosmic lithium problem, which we don't address how that is going to be solved or solved. Okay. What we are quite interested in is lithium evolution in the galaxy. How the lithium from the Big Bang to now evolved. It is evolved by a factor of 4 if I take BBM theory, but if I take the best observational value, which people think this is the primordial value, then the lithium is increased by a factor of 10 from the primordial value to now. Now, in the sense, what you see, very young stars or in the interstellar medium. So this is called the split plateau, which is here. That's called the best observational value, which is basically people think that is the primordial value. And this is the way the lithium evolved over the period. So what are the sources for the lithium evolution in the galaxy? There are a few sources. One is galactic phase. That's spallation reaction, bombardment of high energy particles on carbon and hydrogen particles into helium. That's one of the major components. So other one is in stars. Lithium can be produced in the stars. In principle, the method called Cameron-Fowler mechanism, which was formulated quite a long ago. So basically, these are the equations which can get into. You need to have a C particle like a 3He to get into the beryllium, and the beryllium will be converted into lithium. I will go into this problem later. So, since I said red giants, this is the schematic diagram for red giant stars evolution. Okay, so now you have a one solar mass star which goes into the red giant, and the red giant is this thing which has a inert helium core in the center, and then surrounded by hydrogen burning cell, and then convective envelope. And then as it moves, there is called it's a luminosity bump. And if you see in globular clusters, you can see a cluster of stars there. Okay, and so that's a part of the stellar evolution. Stars evolution gets slower there. I don't want to go into details there. So this is the place that now people think there is some kind of extra mixing is happening, because that is the one which explains the very low abundances of lithium or very low values of carbon isotopic ratios. That I'll talk to later on. So as stars move here, there is a continued convection, and then basically all the elements which were there, like lithium, carbon to nitrogen, these all changes from the main sequence to this place. Keep reducing basically from here. This is called the first stage of it occurs here, somewhere here, this continues here. So here is the place which is called the helium flash, because the entire thing came because when you see in the globular clusters, you see the tip of the RGB, and then there is another, the main sequence which is called red clump or horizontal branch. So to explain those things, and the theory formulated something called these low mass stars develop degenerate cores, degenerate core. And here is the one when the conditions meet, and then the helium starts burning just outside the electron degenerate core, and which produces a kind of like a flashes. The flashes go into energy set a billion times more than sun. But the thing is, you don't see anything outside. There's no observable parameter for this. Okay, so that particular event or series of events can remove the degeneracy in the center, and then make the core as a convective, and then the convective core, and then helium starts burning. So that is the basically red clump stars. But how this happens from here to here, it's not known. We don't have stars in between these things. And then how fast that's going to be happen, we don't know. But then there is a transition from the complete degeneracy to convective. Most of the theoretical models say that around 2 million years it takes. Okay. So though it is almost 60 years back, this theory formulated for the helium flash to here, but then there is no, what is the observable evidence for this? It's happening. So that we don't know. So now get into the lithium synthesis in stars. It's a problem because though stars are thought to be a source of lithium, but there is a problem because none of the standards models produce lithium. That's simply because 3He and 4He reactions supposed to occur at 10 times higher temperatures than what it gets, destroyed. So what happens is when this occurs at a much higher temperatures, okay, then the beryllium has to come, and then the beryllium has to transport it to 7 lithium, okay. So, but the problem is, if you want to survive this lithium on the photosphere, you need to transport it very quickly to the surface. That is not easy there. So that's why the standards models don't predict lithium on the surface of the stars. Once it gets, before it comes there, it gets destroyed basically because of these reactions. Because there are many channels for the lithium for the destruction of lithium. Is that because very sensitive to the temperatures. That's one reason. Okay. So beryllium is unstable and get destroyed quickly before it gets transported to cooler regions where it can be converted to 7 lithium. This is one of the key aspects of it. It is very likely that 7 lithium also get destroyed before it gets transported to upper atmosphere. That is the model which is stood for almost, it formulated some 50, 60 years ago. This is the classical theory. IBA 1967 formulated that much of the lithium gets destroyed as star moves from main sequence to red giant branch stars. Okay, and the main sequence itself is get destroyed before it reaches main sequence. But then, if you have some amount of lithium on the main sequence, but then it moves to red giant, depending on the mass, and then it gets destroyed, a significant amount of it. To put in the perspective, for example, in ISM lithium, you have 3.3. If it doesn't get destroyed, that's what we expect on the main sequence. There are many young stars on the main sequence. They do have something like that. But then when they come to red giant branch, so they become something like 1.5 to 1.8, depending on the mass. That's what the theory. For example, I can quote you typical Arcturus, a typical K giant, which is Arcturus star, which has a lithium in a negative. Look at this, minus 0.6, which is almost like a, 10,000 times less than what you see on the main sequence. Okay. In general, giants show much less lithium than even expected, much less lithium than expected, a factor of 10 less than what is expected. So that's exactly what you see in the observations too. 99% of the observations show the lithium is get destroyed, much more than what the even theory predicts. For example, this I just gave one example here. Look at this is the luminosity versus the lithium here. You can see these are the main sequence stars, and then the stars are going something like this. It is on the red giant branch already. I gave it lithium as a proxy for the temperature here because it goes with the temperature. So then this is the first edge of it occurs. Suddenly the lithium goes down here, serious way. You can just see that one how much. And then it stays back because the convective envelope recedes from the hydrogen burning cell. There won't be any mixing further. So it stays up for some time. Up to this, all the standard models works, even model. But then beyond that, there is a further mixing. This is not even standard models don't have. That's what the extra mixing comes. The new models recently developed. So that is called a luminosity bump. So they explained much more severe lithium destruction, even compared to the stellar models. So that basically lithium is not supposed to survive in stars. That's the key point here. So the observations and theory are in agreement there. But then what the puzzle is in the last 4 decades was serendipitous discovery of one single star, a typical red giant star, discovered by Wallerstein and Steeden in 1982, almost like 40 years ago. In that particular star, you can see this is the lithium normal red giant. And this is the line which has, that is 6707 line, which is a resonance line here, 0 volt line. So you can see that very strong is almost like saturated here. And this is 3.2, which is quite a lot, which is in general, maybe 100 times more than what you see, what you expect from models, what generally see on an average, 1,000 times more than what you see in observational average value. So this is the problem. So they said the lithium could be synthesized in the star and brought up to the surface. That's the issue. But then there are a number of models which couldn't explain it. Then somewhere later, towards 2000, there were 3 proposals came into. One is maybe these stars, there is no mixing. No, there is no sufficient mixing in these things. But that's completely ruled out because what you see from the birth, the original should be 3.3. In some stars, what we discovered was even 10 times more than what is in the ISM. So the thing is, the mixing doesn't hold there. So the mixing is completely taken out because you can't see more than what you see from the birth clouds. And then the new theory came is planetary brown dwarf engulfment because, for example, Earth has much more lithium than our own sun. Say it's like ISM value, and then it doesn't have much hydrogen. Okay, and then when you compare lithium to hydrogen ratio, because we just dump number of Earths into the convective envelope, so you may increase amount of lithium with respect to hydrogen. So that's the one of the things. But then you need to have too many Earth-like things have to go into. So that's also quite unlikely. So, and if that happens, but if it is say the planet engulfment, you should be able to see anywhere on the RGB the enhancement of lithium. Okay, so I will come to that point later. So one of these should be a candidate. That's what we look at it. So where we really got into this problem was we also found one single star. Sometime when I was doing something else, the galactic chemical evolution, we found one star in our list. So that had a typical red giant, but then it has a huge lithium line. And that particular star also has an infrared axis. So that time you had only a couple of them had a super lithium rich, maybe a handful of them classified as lithium rich based on the models. For example, you can see this is when you put what's called a spectral energy distribution, you can see this star has infrared axis. And also this has quite a lot of lithium here. Okay. So this is taken from some survey from IRAS catalogs, led to the suggestion that infrared axis and lithium enhancements are correlated. When the excess comes because of the planet engulfment. When the planet engulfment, it throws away some mass. That mass can be converted to infrared. That's one of the theories that people strongly believe. So there is a merger event for these things. Otherwise, there is no way you can produce lithium. So this is an external phenomena rather than an internal process. Okay. And some of them also found to be slightly more rotational velocities compared to typical RGB stars. That also led to the strong belief that it is an external phenomenon. So what we did was in IAA, because see, getting a high resolution spectra is extremely difficult. Okay, one star at a time, it takes years and years if you want to have a long survey. Till then, we had very few stars, and having any meaningful understanding correlations is extremely difficult. So what we thought, Bharat, I think he's in the audience, Bharat Kumar and myself thought, okay, let us do some large survey, something like 2,000 stars using, so that's only we could do because we have telescopes in Hanley and VPT that can be profitably used for low resolution. And all of this work is much before these all major surveys like Alamos and Gala and things like that. We didn't have the spectra available at that time. So we made use of these telescopes. In 3 years, we got quite a good amount of low resolution spectra. You can see how to derive low resolution spectra. I think this is the first time we applied this survey and then profited very much in this. So this is actually around 3,000, 4,000 resolutions, which has the HCT. I can see the lithium line here. And then we had one calcium line here, some 10 angstroms away from it, which is also 0 volt line. This is also 0 volt line. When I take these 2 0 volt lines, because their sensitivity is the same to the temperature. Okay. And then if I take similar metallicity stars, then the metallicity effect is also gone. Okay. So of course there is a gravity effect. That gravity effect is very small. We're not looking at something like 0.1, 0.05 differences, but we thought of just in the global scenario. So we did some 2,000 stars analysis, estimated, so instead of computing estimated lithium abundances. What we found is completely surprising in the sense, at a particular evolutionary phase. You can just see here, when I plot it here, see this is an entire chart diagram. You can see all these stars, these are some of the previous ones. There are particular luminosities, one place. It's not all over the places. And this is the one led to believe that there is no external source here. Why the planet has to be merged at one particular location of the star? Why can't it be anywhere else? Okay, and this is the first survey we got, large number of stars, almost 13 lithium-rich stars, which almost tripled the that time existing number of stars. So we could say some meaningful understanding of it. So you can see here how the things at one particular place is going on. But then the problem came is that particular place is related to one is a luminosity bump, and also that luminosity bump is one event there, because it seems the core mass increases, then hydrogen bonding cell moves up, and there is an encroachment from the convective cell. That was the extra mixing is going to happen. So our problem came is the place where lithium is going to be depleted extremely. In the same place, you cannot even increase the lithium. That's what our the intuition said something. There's something more to this. So how to solve that problem? And also this is why a red clump, because red clump is a resultant of the helium flash. So the helium flash occurs somewhere here. Okay, there is no way these stars can, even if you produce lithium here, they can't survive here all the way through. But of course, we didn't know these are RC stars or RGB stars. That's one key problem we had. So discovered highest number of lithium-rich stars along with super lithium. No lithium giant well before and after the RGB bump. That's one clear. But we didn't know that time it's RGB bump or something else. But that RGB bump also coincides with the RC space in the luminosity and temperature diagram. One thing clear came is constraint we can put is no planet and brown dwarf engulfment in these things. That's one clear understanding it came. So lithium phenomena seems to be also very short-lived and related to stellar evolution, because now beyond that, you don't have any stars. So that also shows something like this is whatever is happening, and then it's seen for only for some years. Okay. So we also said in that paper, helium flash may hold the key for the lithium production. So, and this is a well-recognized paper in stellar evolution and the nucleosynthesis aspects. And then how do we know this is a bumper? It's a not quite non-trivial issue, actually. So one is, if you really want to know, I take go to global clusters, identify all the, you see this is the bump, and this is the clump. Identify some stars here and some star there and get some spectra. But it is extremely difficult for us because getting that spectra, 18th and 19th magnitude spectra is difficult. So then while searching for this, I have some time.
You have only 6 minutes.
Oh, that's it. Okay. So, okay. So pinning the location really helps. Okay. So either again go to the clusters, doing this with much better telescopes, or I can have a large spectroscopic survey of field stars and then put them in a chart diagram. I can identify which are the bumps and clumps, because you can, though there's going to be a what's called overlap, but that helps. But knowing evolutionary phase of individual stars by some independent, that is astroseismic data. So the last two we used recently, we made use of the latter two. Okay. So one of these things is astroseismic data. So astroseismic data, what happens is normally we are dealt with only P modes, which are on the main sequence, which are people are well versed with that. When you go to the giants, you have a mixed modes. There's a gravity modes also, because the center, the gravity core is much higher. So that also generates certain modes, oscillates. That's called G modes. Those are gravity modes. Okay. And sometimes this gravity and P modes gets coupled. And then sometimes if you are a good spectra, good high signal, high cadence, and then you can even identify almost pure gravity modes, which characterize the core in the center. That's the key. You can see here, all the stars which are down, these are the RGB stars. All the stars which are here, RC stars. You can see this is called a delta P. Delta P is the period spacing between those mixed modes, which is either pure gravity modes or mixed modes. And down we can see the frequencies of, it is a what's called P mode frequencies. P mode frequencies are mostly associated with outer envelopes. And then G modes are mostly the what's the high dense part of it. So a new twist came in this is astroseismic data when we were looking at stars from Lamos, and then we found some of the stars which are also in the Kepler, and then for which then we took spectra from high resolution spectra from HET. Then what we found was surprising. Those two stars happen to be really super lithium rich, and then their cores are, they are not inert helium core, they are helium burning cores in the center. So that means they are RC stars which went through helium flash. So that is the first smoking gun came out of this. So this is, none of these are even RGB stars. They're not in the bump. There are actually red clump stars which pass through the helium flash. So this particular this study then inspired us to go for a much larger survey, which we did with Raghu, and this was also in Abshayal. And then again, the drawback in this is we relied on Lamos, which is 1800 resolutions, but then we only looked at very strong lines, which is almost like a super lithium rich stars. Whatever number of super lithium rich stars we discovered in that, almost 26, all of them found to be core helium burning stars rather than inert core helium, that is hydrogen, that is the red giant branch stars. So that gave a clear picture that none of these stars are even RGB stars, they're all RC stars. So that's one astroseismic data. And then we also used Gala data profitably, and that also showed most of the stars are really RC stars. So they completely shifted the gear. Now the entire RGB is gone, and then only the red clump stars have these what called the lithium enhancement. And this was the final one which we published in Nature Astronomy. This actually we demonstrated actually the lithium only get destroyed along the RGB phase. It doesn't get produced, and then lithium enhancement is common only among red clump stars. And since in between these no lithium stars and the lithium stars, only the major event is occurring in the stellar evolution is helium flash. So probably that is the one which is creating lithium enhancement, but we don't know how it is. Also, we changed the whatever, some 40, 50 years, the lithium limit, the stars which are greater than 1.5, 1.6, that limit now no more valid, because that's not even valid now, because that's basically the standard models. So we put some completely different limit, which is 40 times less than what is theoretical models predicted. So now, since I don't have time, I don't go into models. Then to explain some of our results, and then a couple of theories came up explaining, but they also said these are ad hoc mixing processes. But then we could produce those lithium because through helium flash, the first main helium flash can produce a kind of a mixing that's called helium flash induced mixing, can produce some lithium. So by changing various mixing parameters, they got it. And some of the other theories also came up, neutrino loss and delaying the helium flash on this thing, you can produce lithium. So, and then very lately, recently, and this is going to be even talked by Raghu, and this is a very important paper which we got into. So what happened was, now we didn't know what is happening from helium flash to the RC stage, how to even understand that. So what we looked at was, we used lithium as a chronometer, because it's a very short period, 2 million years, how to get these things. And then we used pure gravity modes from astroseismic data, that's called delta pi. You see a very surprising thing here. All the super lithium rich stars somewhere here, all the these all the red clump stars. All the other stars are here. Very less lithium stars are here, for which the gravity modes are much higher compared to this. That means these are actually the completely RC star. That means the core is fully convective. In between, there is a transition happening from the degeneration to convective. Okay, that's a key. Okay, so the lithium is actually tracking the evolution from a part of degeneration to the convective. So that's a very interesting problem there. I don't go into this. Maybe the Raghu will be talking about this paper tomorrow, day after tomorrow. So we put actually limits there, and that lithium is, as you know, that the red clumps phase is around 100 million years. And it looks like lithium is produced somewhere within 2 million years from the tip of the RGB. So within the 2 million years. So further constraints, we put it with another my student, Anohita Malik. Our post is there, SIG 11. So based on these results, we came to conclusion that when we did a survey, actually you don't see infrared excess in these stars, none of these stars, none of all the RGB stars. Infrared excess is rare among the just giants itself because they don't lose mass. But then many of the lithium-rich giants or super lithium-rich giants, we didn't find much. But then we found 5 stars with infrared excess, but all of them are lithium-rich or super lithium-rich. So there is another smoking gun in that aspect. There is something is happening which we don't know. And there is recently one theory came that there is a white dwarf and then RGB mergers. The white dwarf can just go and sit into the core, and then stars anytime can become RC stars. That's what they say. I'm done actually. Summary. So we demonstrated giant ascending RGB for the first time. Only deplete lithium reaching as low as -1 dex. Lithium excess phenomenon is only associated with the red clump giants of core helium burning phase. And the limit of 1.x classified giants as lithium rich is not applicable for RC giants, as lithium enhancement is common among RC giants. Helium flash is the only major event between end of the RGB and RC phases, imply lithium production during helium flash. Using astroseismology and lithium abundances set upper limit of 2 million years from the RGB with which lithium is produced. IRAS excess is also rare among giants. Most of super lithium rich or do not show infrared excess, but all the giants with infrared excess are indeed either SLR, this thing. So it looks like within 500 or 1,000 years, this lithium is produced during the flashing period. That means the main helium flash. That's actually time, the models predict. So thank you. I'm sorry, I've taken 5 minutes.
1 or 2 questions we can have. Yes, Bani.
Very motivating talk, Richard. I have one question. So all the sites what you are basically mentioning in order to explain the lithium are all stellar based site. So I'm just wondering, is there any other possible sites? I remember about 10 years back, 8 years back, there's a controversial numerical simulation by AGN, and they argued there's a possibility of lithium production even in the AGN.
Oh, yeah.
So it is controversial, I know. So other people argued the PRL paper, and other people argued no, it's not possible. So I'm just wondering, observationally, do you find, first of all, you at all as an observer kind of think of at all any other sites other than stellar star? And second, are you aware of any such observation, some plausibility of lithium?
So what is the spallation thing, which is known, and then people look at that. And then another one is the supernova explosions. During that, people got some spectra of lithium, because that's again a kind of a spallation, because you get a high energy particles, and then they bombard with other heavier elements, they produce lithium. So, but how much that is going to contribute to the entire galactic lithium evolution, we don't know.
But there, in my understanding, problem is, on one hand, huge density, true. On the other, temperature is very high. Yeah. So whatever is being produced immediately would have been dissociated.
Yeah, that's what I don't. They have seen. They have seen in a couple of events.
Okay, Bali. Yeah. All discussions can happen later because we are running out of time. One last question, please. Yes.
I was just curious about the horizontal branch extending. So, because the red clump after that goes to the horizontal branch, am I right? So, in that case, is this seen even in the horizontal branch stars?
Yeah, that's another issue, because for some reasons, we concentrated only low mass stars. That is less than 2 solar mass stars. That's because the helium flash is supposed to occur only in low mass stars, and that is up to 1.9 and 2. Beyond that, the even helium flash doesn't occur because they don't have a degenerate cores. Okay, that's so another problem we are now addressing now. So the stars which are beyond certain temperature, the mostly high mass stars. So
very close to it, you also have the red extending all the way. The horizontal branch extends very long.
yeah, very long. Yeah.
Yeah. So next to that, I mean, closer to that, if the branch extends, I was just wondering if that has been.
Yeah, we need to actually, we are working on those, determining the masses of those stars in the sea. Sure.
We will continue these discussions over tea. So, and I request our online attendees to put their questions in the chat box, which Eswar can answer later. Now we'll move on to our next speaker. Our next speaker is Sourav Bhadra, and he speaks on cosmic rays from massive star cluster. A close look at Westerlund 1. Sourav Bhadra, yes.
So good afternoon. I am Sourav from ISC and I am working as a JAB student in ISM and RI. So today I will be talking about this particular topic, that is the origin of cosmic rays from massive star clusters. And mainly we are focusing on a particular star cluster, that is Westerlund 1 or WG1. So this work have been done under the supervision of Viman Nath and Pratik Sharma and in a collaboration with Siddharth Gupta from University of Chicago. So the first question is, what are cosmic rays? So cosmic rays are actually high energetic particles which moves through space with ultra relativistic velocity. And these are mainly electrons, these are mainly protons and nuclei, and a very small fraction of the cosmic rays are electrons. Now, the common acceleration site of cosmic rays is actually the supernova shocks. And you can see in this video how the acceleration of supernova, acceleration of cosmic rays are happening in the shocks. This is an outgoing shock, and this particle is accelerating in this particular shock, and that got out of the shock. So, and this particular picture shows you the cosmic ray spectrum, and you can see that this cosmic ray spectrum covers a wide range of energy from 1 GeV to 10 to the power 12 GeV. And in our work, we will mainly focus on the 10 to the power 3 GeV and above. Now okay, so as I told you that the cosmic rays are mainly accelerated in the supernova shocks, but some recent detection from gamma rays from various young star cluster like the Cygnus and WG1. So they have given some indication that this particular star cluster can also be another potential site of the cosmic ray acceleration, except the supernova stars. So this is the particular region where we are working, that is the stellar wind origin of the cosmic rays. And recently Siddharth Gupta have already shown that the excess ratio of 22 Ne by 20 Ne in the cosmic ray, that can be explained well if we can consider the cosmic ray are generating from the stellar wind. So all these theoretical and observational background developments project deeper into the origin of cosmic rays from star cluster. So the star cluster gives rise to stellar wind, and those stellar wind creates this bubble-like structure. Now this video shows you how a compact, this is how the WTS, the wind termination shock and the forward shock are forming in a compact star cluster. This video has been taken from Siddharth Gupta. So this blue part is the wind termination shock, and this is the outer shock. So cosmic rays can be accelerated in this wind termination shock as well as the outer shock for the star cluster model. Now I want you to focus on this particular point, that gamma ray detection is giving us the indication of the star cluster as the origin of cosmic rays. So why the gamma rays are so important for cosmic ray studies? So because there are two channel of gamma ray projection in the galaxy. That is hadronic channel and another is leptonic channel. So while their propagation through space, cosmic rays generally interact with the ISM protons and that give rise to pions. Then these pions can decay into two gamma rays. So if we can detect this gamma ray, that can give us an idea about the spatial distribution of cosmic ray proton in our galaxy. On the other hand, in the leptonic channel, the stellar photons can be upscattered to TeV range gamma ray energy by the cosmic ray electrons. So we have studied the both model for our cluster and found that the hadronic origin is much more dominating for the star cluster thing. And this image shows the different. This is coming from a simulation. This shows how the gamma ray luminosity will look like if it is hadronically dominated or leptonically dominated. And our WG1 cluster shows the pattern which is similar to this hadronic origin. So all these things. So for that reason, we have taken only the hadronic contribution, and I will talk about the hadronic contribution throughout the talk. So, and this is the gamma ray luminosity that has been measured above 1 TeV range for the WG1 cluster. So this is the volume and this is the number density. So if we have the idea about the volume and the number ambient density of that particular cluster, we can calculate the cosmic ray energy by inverting this equation. So this L gamma H is the gamma ray luminosity that is coming from the hadronic origin. Now, why we have chosen the WG1 cluster for our study? That is particularly because it is a simple and compact cluster and very simple in morphology. So it can be modeled with simulation, with 1D simulation very convincingly. This image shows the gamma ray maps from the WG1 cluster. And this image has been taken, this image has been produced by using the Hess telescope, which is in Namibia. So this is above 1 T, and this is above 1 TeV range. Now, there are some other clusters like Cygnus, but those have some morphology, some non-spherical morphology, and that cannot be modeled with the 1D simulation very easily. So that we have not studied yet. Now, this table shows you the various parameters of the particular WG1 cluster, the extension, age, kinetic luminosity, distance, and mass loss rate. Now, coming to our work, what we have done. So, as I told you, this is the schematic diagram. So we have injected cosmic rays in this central region as well as in this wind termination shock and the forward shock. So in the central region, we have defined that epsilon CR, which denotes how much of the total energy is going into the CRs. If it is 0.1, that means 10% of the total injected energy by the star cluster is going to cosmic rays. And by shock injection, we meant that we have injected the cosmic rays in the shock portion, and this WCR denotes how much of the total downstream pressure is going into the cosmic ray pressure. So these are the used nomenclature for the defined injection method, and this epsilon CR and WCR, we will call them as injection parameter. So also we have used the combined injection, that is the injection in the central region as well as the injection in the shock region, that has been named as the combined injection. So for the central region, one thing will happen, that cosmic rays will be injected in this particular region and then they will move outward direction. But in the shock injection, the cosmic rays will be injected in this shock and in this shock, and then they can move outward as well as inward from the particular region where they have been injected. We have used for our simulation, we have used Pluto, that is the hydrodynamic code, and which supports CR. So these are the main some important things of the simulation. We have used radiative cooling, CR diffusion, and as ambient medium, we have used uniform as well as radially varying. So this plot shows the radially varying ambient medium. And as I told you that we have used the central injection and shock injection. And where required, we have also used the time varying luminosity instead of a constant luminosity and the thermal conduction. Now coming to our result, this is the main result of our simulation. So I will draw your attention to the particular thing, that is this plot. This plot shows the CR pressure and densities. This red curve shows the pressure and the blue curve shows the density as a function of radial distance. On the other hand, all the other plots shows F as a function of projected distance. I will come to those, like the second and third plot respectively shows the projected gamma ray luminosity and projected mass as a function of projected distance, not the radial distance. That is the important thing. because in observation, always the measurement happens in projected distance, not the true radial distance. So these 5 black points are coming from the observation. So if I show you, you can see that in observation, the WD1 cluster has been divided into 5 different annuli with equal width, and those black points shows the value of every annuli. So you can see for the for the central injection method, we are getting a good match with the gamma ray luminosity and with the projected mass. Although the CR energy density, we are not getting a good match. Now, how the CR energy density has been calculated from the observation? That is actually, they have divided the projected gamma ray luminosity value with the projected mass value with some additional factors. So this gamma ray luminosity and mass are the observed quantity, not the CR energy density is the direct observed quantity. It is calculated from these two observed quantity. I mean, it is dependent of these two things. On the other hand, this particular plot is coming from only simulation. There is no dependency on the gamma ray luminosity or projected mass or anything. So you can see for the central injection as well as for the shock injection, with the proper choice of parameters, that is the diffusion coefficient and the injection fraction, we can explain the observed gamma ray luminosity and projected mass. And you can see that in the central injection, the cosmic rays are going outward from the center, and for the shock injection, it is going inward into the bubble as well as outward from the bubble. Now, we have also studied another injection method, that is the multiple supernova injection. So why this is because as it is a cluster, there are numerous number of stars, and that will go undergo the supernova after a particular time. So we have also considered that method here, and with the proper choice of parameters, we are also getting a good match with the gamma ray luminosity and the projected mass for this multiple supernova thing also. Now, in this paper, Aharonian et al., where they have observed from where the data has been taken, so they have mentioned that you need one supernova in every 1,000 years to explain this gamma ray luminosity and projected mass. But we have calculated the frequency of the supernova in that particular cluster, and you can see we need we don't need this much high frequency of the supernova. One supernova in every 0.03 million years is sufficient to explain the observed gamma ray luminosity and projected mass. So, and this plot is coming from Abesekara et al. Paper. So I would like you to concentrate on these 4 green points. These green points are actually the cosmic ray density above 10 TeV for Cygnus cluster. It is not for the WD1 cluster, but you can see there is a uniform distribution, not a radially varying distribution that Aharonian paper is getting. And this Abesekara data more fits with our simulated data, that we are also getting a uniform profile of the CR energy density, not a radially decreasing CR energy density. So the main takeaway is that this projected profile does not actually tell you what the radial profile of the CR energy density is, because you can see the true radial profile is very different from the projected profile. And from this projected profile, you cannot correctly say what the radial profile is. Okay. Now, this is the main thing of our paper, and the projected profile can be explained by the proper choice of parameters also. These parameters are not at all arbitrary. These are consistent with the previous works. So using those parameters, we can explain the gamma ray luminosity and projected mass also. Now, briefly, I will tell about this. Till now, I will not go into this plot. Till now, I have told about the gamma ray luminosity, but we have also measured calculated the X-ray luminosity from our simulation, and you can see using TC means thermal conduction. Wherever there is thermal conduction exists or not, the stellar wind model, which is this blue and this red, can explain the observed X-ray luminosity. This gray band is the observed X-ray luminosity. Whereas to explain the X-ray luminosity, we need the thermal conduction for the multiple supernova case, because without the thermal conduction, we cannot explain the X-ray luminosity. So our model is also consistent with the X-ray luminosity as well as the gamma ray luminosity of that particular star cluster. So, okay, so this was the conclusion you can go through. So, and I will again emphasize on that point that it is not needed that the projected profile will give you the true radial profile of the cosmic ray energy density. And that is the main crux of our paper. And we can explain the observed gamma ray luminosity with any of the injection method. That is the central injection as well as the shock injection. So we cannot say from the gamma ray luminosity observation that whether the cosmic ray are accelerating in the only shock or in the central region. It can accelerate in any position. Okay, so I will stop here. And
Thank you, sir. For a very I have one question. What is the source of your 20 neon and 22 neon?
oh, that I have taken from just a second. Yeah, this one. This is the observed value of the 22 NE/20 ratio. So this green line is the observed value. So using the star cluster thing, that black dot, more black line, not the gray one, the black one, you can explain the data. Where the gray one is coming only from the supernova.
We can have a quick question from the Zoom attendees. Is anyone there? Okay, so we'll move. Thank you, Sourav again. Now we'll move on to our next speaker. Our next speaker is Vipin Kumar, and he speaks on exploring the short-term H-alpha variability in a sample of M Dwarfs. Vipin.
अच्छा डिटेल से स्लाइड शो में आपका वो है दे दीजिए तो पीपीटी उसे ये बड़ा होता है वो इसको यहाँ से मैं नहीं पीडीएफ होना चाहिए इस पे नहीं होगा ज़ूम पे नहीं सॉफ्टवेयर
With the PowerPoint presentation, maybe Yes, the system is coming up.
Room number 104, all are ready. Kindly share your screen.
Devendra, can you please share your screen?
Can anybody from the volunteer confirm for the sharing?
Can you send a message to him? Read messages. Or maybe we can call our online. You are ready? By the time of the okay, okay. So it does come in another minute. Go back. Maybe you can.
Hello. Hello. Am I audible? Hello. Hello. Am I audible now?
Yes, you are audible. Please go ahead.
Okay, I am sharing my screen. Okay. Can you see it?
Yes, yes.
Okay.
Perfect.
Good afternoon to all of you. Myself, Devendra Bisht, and first of all, thank you so much for giving me an opportunity to present our research work. Today, I am going to present our recent work, a deep study of an intermediate age open cluster SAI 35 using ground-based imaging and Gaia EDR3 astrometry. First I will discuss some motivation of behind this work. To understand the star formation history and the structure of the Milky Way galaxy, and open cluster are good tools to analyze properties and the structure of galaxy, and so constitute a principal link between theories of stellar evolution and observable universe. And the most important thing is that the initial mass function aspect. So is the initial mass function is universal, or how initial mass function vary with in different environments or with different parameters. So this is one of the most important aspect. And the ages of young clusters, say few millennia, are small in comparison to their dynamical evolution time. So it's so their position in the galaxy represents the location of star formation. So we have taken observation for this object on 21 January 2010 using 104 centimeter Sampanana telescope located at Aryabhatta Research Institute of Observational Sciences, Manora Peak, Nainital. So images were acquired in 2K by 2K CCD, and this is log of observation table. We have taken some deep exposure frames in UVVI filter, and this is simple flow chart after taking CCD images, how we have done the data reduction procedure. This is simple thing. So normally after taking the, data from CCD, then we do some procedure, pre-processing, processing, and post-processing. In pre-processing, our main aim to clean the raw images, and for that we have used IRF software. In processing, to get the instrumental magnitude, and we have used Downward software for that. And in post-processing, our main aim to find the standard magnitude, and for that we have used Downward software. And apart from this observational data, we have used several other publicly available data sets. We have used Gaia EDR3, which contains the position, parallax, and proper motion. with a limiting magnitude of 21. And it's the sovereign listed radial velocity data for plenty of clusters using Gaia EDR3 data, but this object is not listed in their catalog. So for radial velocity measurement, we have used Lamos VR5 data set. Lamos provided 9 million spectra with radial velocities in its fifth data release. And we have used this data to obtain mean radial velocity and metallicity towards the region of SAI 35. And other photometric data sets, we have used APA-SS to compare our photometric data with this catalog. And this is, you can see the comparison of our data with APA-SS. And we have also given some values in the table in the difference in magnitude and the difference in color. And in bracket, their standard deviation is showing here. So this comparison is basically that we find the fair agreement. So proper motion and vector point diagram. So proper motion means simply the changes, the star changes its changes apparent position as seen from the center of mass of the solar system. So proper motion, basically the importance of proper motion is to find the membership probability of stars, as well as to the second thing, and the second one is to find the true space velocity component. So space velocity is the combination of transverse velocity and the radial velocity. So radial velocity can be estimated using spectroscopic observations. So here we have used the Lamos data for radial velocity measurement. And this is the vector point diagram, and the left side is the entire sample. This is on cluster sequence, and this is the field motion data. And we draw a circle of 0.6 million arc second per year, and this circle is a actually this chosen radius is a compromise between losing member with poor proper motion and contamination of field region stars in this area. So, and we have also used parallax for the selection of cluster member, and a star is considered as a probable member if it is lies inside this circle and has a parallax with 3 sigma from the mean value. So after that, we have also estimated membership probability of those stars, and we adopted the approach given by Balaguer Norris, and we have used proper motion and parallax data from Gaia EDR3. So according to this method, the stars, the distribution of star can be explained into two different ways: the cluster star distribution and the field star distribution. Where the different notations have their usual meanings. And here mu xc and mu yc are the mean value of proper motion, which is listed here. This is the mean value 1.10 and minus 1.66. And the sigma c is the proper motion dispersion. And proper motion dispersion we obtained at 0.09. And we have also estimated the mean value of proper motion of for field region stars and their dispersion, which we found these values. So we used all these values to find the membership probability of stars. And this is basically the total distribution of stars, phi equal to nc into phi cv plus nf into phi fv, where nc and nf are the number of cluster member and field members, and phi cv and phi v are the distribution of cluster and field region stars. So finally, membership probability we estimated dividing the cluster distribution divided by its total distribution. So here, after estimating membership probability, we have plotted those members here. So you can see here we have plotted V magnitude versus probability, and how we separated field region stars. So these are field region stars and these are cluster region stars. So we considered above 0.5 stars which have membership probability higher than 0.5, we have considered those as a probable members. And this one is also V magnitude versus mean parallax, and this horizontal line is the indicates the mean value of parallax. And this is clean color magnitude diagram, and here the distribution of stars, right? This is identification chart, and this is the distribution of star in proper motion, and plus sign indicates that the mean value or the center coordinate of position and the center coordinate of proper motion. So clusters orbit near the galactic plane. So they are constantly disturbed by tidal forces, which originating from originating from galactic disk and the molecular cloud present there. Due to this disturbance and dynamical evolution, the structure of open cluster gets changed. So the importance of cluster orbit is to understand the effect of tides as well as the evolution and formation of stars and galaxies. So to understand orbital picture of this cluster, we adopted the model given by Allen and Santillan. According to this model, mass of a galaxy can be described into three subsystems: the spherical central bulge, disk, and the massive spherical halo. So all the constant using in these potential equations, we have taken these constants from Paskova and Bobilev, and we have used all the input parameters which we have estimated in this paper, and we obtained the different orbital parameters as listed here in this table. And we have also plotted the orbital picture. This is the side view of the orbit, and this is the top view, and this is motion of cluster in the galactic disk with time. And the triangle and dot indicates the birth position and the present day position of this object in our Milky Way galaxy. And we obtained the eccentricity value as 0.01, which is nearly zero. Hence, we can conclude that these orbits showing boxy pattern, and they are orbiting a circular path around the Milky Way galaxy. So radius is very important parameter to obtain the more reliable cluster fundamental parameters. So first we draw so many concentric circles around the cluster center like this, and to obtain the density in each annulus. Density is annulus number divided by its area, and then we plotted this density versus radius. And after a certain point, this cluster density merged into field star density. You can see some flatness started from here. So we choose this point as our cluster radius at 3.9 arc minute. And we have also fitted King profile to our observed radial density profile. According to the King model, three parameters are required to discuss the structure of a cluster: core radius, tidal radius, and richness factor. Core radius, we obtained here 1.2 arc minute. Core radius is the point where central density becomes half. And tidal radius is the distance from cluster center where gravitational influence of cluster is same as gravitational influence of galaxy. And we used this method given by Gengel and Towns, and a formula given by Kim et al. We have used this method to find the tidal radius of this cluster, and we obtained tidal radius as 10.22 plus minus 0.82 parsec from here. And this is our identification chart, and this is showing this inner circle is core radius, and this is the radius of this circle, 3.9 arc minute radius. So reddening and two-color diagrams. Reddening is important parameter to understand intrinsic properties of cluster star. Reddening occurs because of absorption and scattering of in the interstellar medium by the dust particle. So in the absence of spectroscopic observations, we generally use B minus B, U minus B color diagram. You can see here, we have used only probable members, and we fitted zero age main sequence. The solid line is the zero age main sequence given by Simit Keller. And this solid curve, we have taken this solid curve considering the slope of reddening EU minus B and EB minus B as 0.72. So from here, we estimated a reddening value at 0.72 magnitude. And we plotted different various color diagrams and find the slope. Actually, we are checking the extinction law towards the cluster region. So that's why we have used these various color diagrams, and then we estimated total to selective extinction ratio. Our cluster is this, and our value obtained as around 2.9 to 3.3, which is very close to the normal value. Then we conclude that this cluster showing the normal interstellar extinction towards the cluster area. And age is very important parameter and we can estimate age in various methods. So here we have used isochrone fitting method to find age of this object, and we fitted isochrone given by Marigo et al. We plotted isochrone of 8.5, 8.55, and 8.6 log age. Here, a solid the black dot are the probable cluster member. Our probable members in this study, and blue one are we have also matched our membership probability, membership catalog with the Canton Goodin catalog. So these are the matched stars. Blue one are the matched stars. And we also detected one BSS member here. You can see here, this is the one possible BSS. BSS are interfering of object in diverse environments such as open clusters. And BSS are found along the extension of the main sequence as the brighter object than the main sequence turn off points. So they are very crucial object to study the interplay between stellar evolution and stellar dynamics. So we found this BSS at a distance of radial distance of 2.2 arc-minute from cluster center, and this is confirmed cluster member with membership probability of 99%. And after fitting theoretical isochrone, we also obtained from here distance using distance modulus. So we found around 2.95 kpc distance from here for this object. And we have also estimated distance using parallax of those stars. So this is, you can see the black one are the all stars towards this area, and the red one are this one. These one are the only probable members with membership probability higher than 50%. So we also fitted Gaussian profile into this to find the mean value of parallax, and the mean value is obtained as 0.35 plus minus 0.0. So from here, distance we obtain distance is 2.9 kpc. So initial mass function, the mass function we described.
You have 1 more minute to go. Sorry to interrupt.
Mass function. So initial mass function, the first quantified and well established by Edwin Salpeter in 1955. They have used stars more than one solar mass, and they found slope is around 1.35 for those stars. Miller and Zylo extended his work for less than one solar mass, and they found slope comes to be 0. So many astronomers came into action, and they estimated initial mass function for many clusters. But we are not in a position to say that it is. We have estimated we often the luminosity function diagram of the stars. So for first, we also obtained the study the completeness of CCD data, because we may not detect all the stars present in the CCD frame due to the stellar crowding and inefficiency of the CCD data reduction program. So we have randomly added a few artificial stars into our science images, and we have done the data reduction procedure as a similar manner as was done for the original images, and then find the completeness factor in each magnitude bin, as you can see here. And we applied these completeness factor to find the luminosity function, and we have used mass luminosity relationship to convert luminosity function into mass function, and we found mass function slope as 1.49. And using this mass function slope, we also estimated total mass, which is 364 solar mass. And we have also estimated total relaxation time of this object. Relaxation time means after exchanging energies between two members, they approach their velocity distribution approaches to a Maxwellian equilibrium. That is what we call dynamical relaxation time. And dynamical relaxation time is coming 11 million years, which is very less than cluster's age, this age of this object. So we can say that this object is dynamically relaxed. And we have also checked mass aggregation effect. Mass aggregation basically because of the equipartition of energy amongst the cluster member. Because during close encounter of two members, they stars exchanges their energy and momentum. So energy can be exchanged in either direction. So there is a statistical tendency to utilize kinetic energy during an encounter. This is statistical phenomenon known as equipartition. So in mass aggregation,
quickly wind up now.
I am finishing it. Yeah.
Okay.
So we have distributed clusters area into 3 different mass ranges, as you can see here, and plotted cumulative radial density profile. So we can see easily here the massive stars are centrally concentrated, and lower mass stars are lying towards the outer side of this cluster. And we have also confirmed this using Kolmogorov Simonov test to see the statistical significance, and we found the confidence level at 90%. And this is conclusion. We have also compared our data with the literature, and our values are very comparable. We detected one PSS member for the first time in this object, and we have estimated total mass as 364 and mean mass 1.7 solar mass, and is obtained as using theoretical isochrone given by Mariko, and our distance value from fitting is also coming same as using mean parallax of this object, and this object is dynamically relaxed, and this study concludes that this object traces a circular path around the center of the galaxy. Thank you so much.
Thank you, Devin, for a very interesting talk. We'll have a quick question and then we'll move on to the next question. We'll wait for that. Yes.
Devin, you have taken.
Yeah, hello.
Segregate the cluster member with the field member. You have taken a membership probability of 0.5, right?
Yes.
So this will be liberal because people take even 80% probability. So have we checked between say 50 to 80? Because often people take 60, 70, that kind. So you have taken a very liberal approach to segregate the cluster members. So have we checked these members between 50 to say suppose 80%, where they are really the cluster members, or they are quality in your color magnitude diagram, color diagram, all these?
Actually, we have tried that. We have checked the color magnitude diagram after using stars massive than 80% probable stars, but we found that many stars were losing in the main sequence area actually. So that's why we, for safe side, we have used we have used stars with higher than 0.5 probability.
No, but it is not just color magnitude diagram. You have to look into the color diagram also. I mean, their parallax preference. A lot of things you have to check because even you will find the color magnitude diagram, the field members. It is similar type of as you see in the cluster. So color magnitude diagram is not the criteria to just segregate the cluster member and field star.
Yes. Yeah, I will check that. Yeah, okay.
Okay, Devin, I will take one question from the online. Arpita, go ahead and ask your question. Unmute yourself, please.
Yeah. Hi, Devin. It's a nice talk. Actually, what I was wondering that your cluster mass is of the order of 300 to 400 solar mass, and if that's the case, probably your IMF might not be finely sampled. There will be there'll be highly stochastic. And in that case, how do you really conclude on the IMF? Because for the IMF sampling, for fine sampling, you need a mass of the cluster of the order of 5,000 solar mass or above.
But this is not very massive cluster actually. This is not massive.
Yeah, that's what I'm saying. So that means that IMF is not finely sampled. Probably it's highly stochastic.
Yeah, yes, you are right. Yeah.
Yeah, in that case, so how do you conclude on the IMF?
Actually, this is we can say that this is present day mass function. We are calculating. So we have used the star up to around 20 magnitude in V band for the calculation of initial mass function. So we have used the star up to 20 magnitude. So actually, this is not very massive. So we can't get mass in the order of thousands actually for this object.
Yeah. So that's what is my question. Then how do you conclude about?
Okay. In the interest of time, we will put some limit.
Okay.
We'll move on to our next speaker, and our next speaker, I think we'll go back to.
I am the next speaker. So I'll just share the screen.
Arpita, okay. Go ahead, Arpita. Fine. I think we'll get
Yeah, I am the next speaker. I'll share the screen.
All yours.
Can you see my screen?
Yes.
Good. Okay. Is it all right?
Yes, perfect.
Okay. So I'm a postdoc at Scuola Normale Superiore Pisa, Italy, and this work has been done when in my first postdoc at Australian National University. And here I'm going to talk about, in collaboration with these people, and here in today's talk, I'm going to talk about a new mechanism for the origin of WNL stars. So as I go along, I'll say what are WN stars and WNL stars and etc. So anyway, to start with, these are nothing but like massive stars. So why are we so much interested in massive stars? Massive stars, even though they are less in number compared to their low mass cousins, they are the major sources of ionizing photons, yields, chemical yields, and mechanical luminosities. So whatever major aspects of the astrophysics that you study, be it from the stellar evolution models to population synthesis codes to spectral synthesis to galaxy evolution and formation, and which are the subset of cosmological simulations. If you want to study the chemical and ionization evolution of these of galaxies or the cosmological over cosmic time, then you need to, and not only that, also the gravitational waves. So if you look at the neutron star or the black hole, the progenitors are massive stars. So you understand that for the majority of the astrophysical problems, the majority of it is highly dependent on how well we understand the structure and evolution of massive stars. Okay, so when we talk about massive stars, we cannot we cannot not talk about Wolf-Rayet stars. So as the massive stars evolve during the end of their main sequence, and when the core is helium burning, we see this huge amount of mass loss. And this phase is particularly known as the Wolf-Rayet phase. And and spectroscopically, normally how you determine this Wolf-Rayet phase is that you see these very vibrant and broad and strong emission lines. And that is very different from the typical narrow absorption lines that is observed in the normal stars. So normally these Wolf-Rayet stars are subclassified into two classes. That is WN stars, when the surfaces you see the helium and nitrogen lines, and when you see the helium, carbon, and oxygen lines, you call them as WC or WO stars. Now these WN stars can be again subclassified into two categories. One is WN, depending on the line strengths of different excitation lines, whether you are seeing the higher excitation lines or the lower excitation lines. And early type WN stars are normally when the core is helium burning and surface temperature is quite high, you see the higher excitation lines, whereas the late type, when mostly, although there is no proper definition of, the definition is quite convoluted, but still mostly they are towards the end of main sequence, when the surface temperature is not as high as WNE stars, and you see lines like helium-1 and nitrogen-2, nitrogen-3, but not the higher excitation lines. So now, if we want to model these stars, in our model, we use the MESA 1D stellar evolution code, which is modules for experiment in stellar astrophysics. And actually, we use the more realistic version of MESA, which is more realistic for the massive stars case, which is MIST, that is MESA isochron stellar tracks, and that also has different versions. We use the MIST2 because that takes into account the more realistic abundance pattern. So in our stellar model grid, this is for especially for this work, we have pretty decent grid with mass ranges, with mass rotation rate and the metallicity ranges, quite good ranges of them. And now, if we look into the structure of massive stars, in the left-hand panel, what I'm showing is the cartoon of the massive stars, and here the color-coded based on the helium mass fraction on the main sequence, during the main sequence. If you look at the massive star, you see there is a huge convective core where all the chemical elements are quasi-chemically homogeneously mixed. And then there is a radiative envelope, and then the very thin outer convective layer. So whatever heavy elements that are being cooked within the very small inner core, that is being convectively, almost chemically homogeneously mixed within this convective zone. But the question is, how do you transport these elements, heavy elements, from the inner core to the outer surface? Now, when on the right-hand side, what I'm showing is the diffusion coefficient as a function of mass at different radii for 100 solar mass stars at a time when it has already lost 20 solar mass. Now, you can see that when you have rotation, you have different rotational instabilities, and and due to those instabilities, you have this mixing of chemical elements, and that helps in dredging up these heavy elements from the core to the surface. I'm not going into the details of these different rotational instabilities. If you have queries, you can ask me at the end of the talk or later on. I'm happy to answer. So, but the question is like, okay, now if you have rotation, you can transport these elements from the inner convective core to the outer convective zone. But if you don't have rotation, do you really see high mass fraction, surface mass fraction of these heavy elements? And if you see, how do you transport the elements from the core to the surface? That's the question. Now let's directly dive into our some of our model results. And here I'm showing you the surface helium mass fraction as a function of rotational velocities and as a function of time during the main sequence, and for 3 different masses and 3 different metallicities. As you can see that if you have the stellar rotation rate, which is almost 40% or 40% of the critical velocity or more, then you see that towards the mid to end of their main sequence, you see surfaces enhanced, or you have surface helium mass fraction, which is more than 40%. So they have already entered the WNL phase. But the question is like, but if you look into these slow rotators or non-rotating stars, then also if you have masses which is pretty high or the metallicities which is high enough, then you see that towards the end of their main sequence, they enter this WNL phase, when you have surface helium mass fraction almost of the order of 100% as well in some of the cases. So the question is, do we really observe this kind of stars which have WNL-like features, but they're slow rotators? Yes, we do observe. Now there are different observations. You can measure their velocities based on Doppler shifts or like fitting, even sometimes fitting the absorption lines of H alpha, H gamma, or sometimes by the spectropolarimetry. But whatever be their method for calculating the radial velocities, you see that the velocities are they're slow rotators. They're almost 100 or 120 kilometers per second, and they show these WNL-like abundance patterns on their surfaces. Now the question is like, if they are slow rotators, how can you have surfaces enriched with heavy metals? Heavy elements, I would say, because helium is also included. And now in the early 2000, the experts in this field, like George Manning and Mayday, they tried to come, they came with the hypothesis. What they hypothesized was that probably these stars, what you are seeing today as slow rotators, they started as fast rotators. And when they were the first rotators, all this chemical mixing had happened. And as the stars evolved, it lost its mass, and thus it lost its angular momentum. So today you are seeing them as slow rotators. But whatever surface element abundances you are seeing, that had happened when they were fast rotators. That is a pretty feasible and viable explanation for this surface enhancement in the slow rotators. But then, is this the only mechanism? That's the question. Had it been the only mechanism, then we wouldn't have seen the surface enhancement for the non-rotating cases. Right, so there has to be a new mechanism for the surface enhancement. So I know that you are towards the, like, you have had a very exhausting day, and you are almost about to miss your coffee break. So I'm going to just sit back and relax. I'm going to show you some of the movies. Okay, so now, if we come to this new mechanism, what you call this mechanism as exposure of fossil convective cores, what is actually happening is that as the stars are losing more and more of its mass, it's actually contracting. As the star is contracting, it's exposing more and more of its inner convective core, but that's a fossil convective core. That's what we mean by the fossil convective cores is they are no longer convective at the current time, but they were part of the convective core at an early stage of star's evolution. Okay, so now, before I show you the movie, let me just tell you, in the left-hand panel, what I'm showing is again the diffusion coefficients for the non-rotational mixing mechanisms, and as a function of Lagrangian mass, and also like on the y-axis, also I'm showing the helium mass fraction. Now, at some time, I've chosen a time at what time you see the central helium mass fraction is almost 30%, but the surface is not yet enhanced with the 30% helium mass fraction. So the question is, at what time does it get enhanced, right? So now as I play the movie, as I go to the next snapshot, what I'll do, I'll just pause after the next snapshot and I'll explain you. Okay.
You have 2 more minutes.
Yeah, I'm almost about to end. So what you are seeing is that I'm going to show all the old time values as the faded lines, and the current time values as the dark lines. And on the right hand side, it's again the cartoon based on the helium mass fraction color coded. And now as you move in time, you see the star is losing its mass, it's contracting, but the surface is not yet enhanced with the 30% helium mass fraction. But as soon as the surface gets superimposed with the fossil convective core, you see the surface helium mass fraction gets enhanced to 30%. Let me play the movie again. The star is losing mass and it's contracting, and as it's contracting, as soon as the surface falls on top of the fossil convective core, you see the 30% surface enhancement. So the same I can show in the another case when the surface gets enhanced to the 40% case. And you can see the star is losing its mass and it's contracting. And as soon as the surface falls on top of the fossil convective core, you see the surface gets enhanced to 40%. Now, the question is, whatever be the surface enhancement mechanism, can we really produce the synthetic spectra that matches the observed spectra? So there are these 3 are the observed spectra, 3 red lines are the observed spectra, and the black one is our synthetic or the model spectra. And the right hand side, we are showing the same spectra for a larger wavelength range. And you see that our spectra matches pretty well with the broader helium-2 line and also the nitrogen 4 emission line. So here we can conclude that we have actually we have modeled our WNL stars pretty well. Okay, I'm not going into the details of how badly sometimes people model in the stellar atmosphere modeling and what can be its implication. So with that, I'd just like to conclude that massive stars evolve into the WNL phase with very high surface helium and nitrogen mass fraction if they are rotating, and also it's possible if they are non-rotating but they are almost like at solar metallicity and highly massive, like almost of the order of 100 solar mass and above. And this mechanism, when they're non-rotating, we call this as this new mechanism of WNL star production. We call this as exposure of the fossil convective core. This provides a natural explanation for the origin of slowly rotating WNL stars, where you don't need to invoke this rapid or the havoc stellar spin down scenarios like it was proposed in the early 2000s by Many and Mader. And also, depending on how well we produce the spectra, that has huge implications on what will be the ionizing photon budgets in different ages. It doesn't affect much the hydrogen ionizing age, but it affects the it highly affects the harder photons, which are the helium-2 and oxygen-3 ionizing fluxes. And they can be, depending on how well we model, they can be affected by a factor of 20 less or more emission fluxes. So with this, I would conclude, and I can just say that this is a pretty novel approach, or the pretty novel method to produce slow rotating WNL stars. And yeah, thanks for your patience listening.
Thank you, Arpita, for a very interesting talk. We'll take a couple of questions.
Sure.
Any questions? Okay, I have a quick question. You were talking about this WNL stars, and
yeah,
I don't see any hydrogen lines in your spectrum.
Yes.
Why are there no hydrogen lines?
Yeah, that's right. You see very little. Okay. you see very less like kind of very weak H beta absorption lines, but not much. Yes, because these stars are losing its mass pretty exotic mass loss it's going through, so it has lost almost all
I
of
get
it.
you. And the quick question is, you talk about metallicity, and what determines hydrogen abundance there? You talk about Fe by H.
Yes,
You
right.
determine hydrogen abundance from this weak bump H beta, which I think is heavily blended with helium 2.
Yes, that's true. So what I'm trying to say is that if I understand your question correctly, is that okay. What I'll say is that it's heavily blended with helium-2. That's right. And if you are talking about hydrogen lines in this, okay, can you please just repeat the question again, if I'm understanding it correctly?
I think in the interest of time, it is very difficult to get hydrogen abundance here. I will move on to next speaker. I think we'll discuss.
Yes.
Okay.
Yeah, we can have the hydrogen abundance if you have pretty low metallicity, but this one is at LMC metallicity, which is 0.3.
Yeah,
if you were 0.3 or 0.5.
Yeah, very interesting talk.
Yeah.
There was one more question in the chat.
I think you please look at the chat and accordingly reply. We'll move on to the next speaker.
Sure, thanks.
Thank you, Arpita. Okay, our next speaker is Vipin, and Vipin talks on exploring the short-term H-alpha variability in a sample of M Dwarfs. Vipin.
Yes. It's not working properly. It's not coming. No, it's not coming. No. So open PDF and I scroll and then. Yes, this one. Just go here. There is an option for this one. No. It's copy.
अरे हाँ ये बहुत पुराना होता है। चलिए ठीक है, उससे तो बेटर।
All set?
हाँ इसमें
नहीं जा रहा। अरे हाँ
वो फुल स्क्रीन नहीं हो रहा उधर से, यहाँ पे शेयर्स
ये
So I think you
No,
please
I
go
think,
ahead with
yeah.
this.
So, hello everyone. So today I will talk about the short-term H-alpha variability in a sample of M Dwarfs. And these are my collaborators, Juchert and Juchert from PRL. So these are the outlines of my talk, in which first I will give a quick introduction of M4 instrument, which is mounted on PL 1.2 meter telescope. Then I'll come to the studies of M Dwarfs using M4 instrument, and then I will talk about the H-alpha emission in the M Dwarfs and their variabilities. And also I will talk about the variabilities as a function of the spectral type, the rotation period, and the star spot filling factor. And then I'll summarize my talk with the future perspectives. Okay, so let me start from the very beginning of my PhD work when as a first project, I started the assembly integration testing of this M4 instrument. So there are the three pictures. The left one shows the PL 1.2 meter telescope on at Mount Abu, and the middle picture is taken during the assembly of this M4 instrument, and the last picture is the M4 when it is mounted on the PR 1.2 meter telescope. So these are some specification of M4 instrument. So it is basically meant for to do the imaging as well as the low resolution spectroscopy in the optical domain. So initially I have started the studies of M Dwarf using M4P as a characterization program of M4P instrument. You know, when you build an instrument, then you have to do some characterization work, and one of them is the performance verification. So to do the performance verification, I have choose these M Dwarf objects because they are easily available in the sky and of different magnitudes and different spectral types. So I choose them. So who are not familiar with these M Dwarfs? So what are these M Dwarfs? Basically, these are the coolest and lowest massive stars in the chart diagram. If you want to find them in the chart diagram, so you can see in the left right bottom part. So we are coolest. They are very cool. The temperature roughly ranges from 2300 Kelvin to the 4000 Kelvin, and they are less massive also, 0.075 solar mass to 0.6 solar mass. And they are also most populous stars in our galaxy. Now come to the significance. What is the significance of these objects? As I said that they are less massive, it means they evolve slowly in the main sequence and take much more time to stay in the main sequence. So these stars are the good tester of the galactic history, and also there is a great significance of exoplanet searches to especially to explore the planet in the habitable zone. Now come to this spectrum that which is the characteristic spectrum of any M dwarf. So this is basically M3 spectral type of the M dwarf, and you can see several TIO bands are there, which are the absorption bands, because the temperature is very low, so they can sustain and gives these absorption bands. So this particular TIO feature is the key characteristic absorption bands, which can categorize any star into the M dwarf. Now, as I said earlier, that I have started the studies of M Dwarf as a performance verification. So this was that project which I have published already. And in that project, we observed the 80 M Dwarfs. In that observation, we found in the 10 sources, they are showing the H alpha. And then we have realized that, okay, these are the active M Dwarfs, which shows the H alpha chromospheric emission. And the variability in this H alpha emission is the indicator of magnetic activity. After that, we explore that any H alpha variability program is there in the literature, and then we have found there are some very few studies which have targeted the H alpha variability in M Dwarfs at shorter time scale. Then we have decided to do the statistical study of short-term H alpha variability at shorter time scale in the M Dwarfs. So before going to the observation part, I would like to discuss that what are the role of H alpha emission in the M Dwarfs. So basically, the magnetic activities is the general term to describe any observational phenomena like strong stellar winds, flares, coronal mass ejection, sports, etc. And these magnetic activities are closely tied with the rotational period. So how can measure these two things, the activities and the rotational period? So the measurement part, if you want to estimate any rotational period of the star, then you have the two options. One is the V-SAN measurements, which we can do with the spectroscopic data. And another one is the photometric light curve. So with the photometric light curve, you can measure the brightness variation and you can find the rotational period. For the activity strength, you have to do some proxy for that, which is the coronal or chromospheric emission, in which and you can check their temporal variation and you find the activity strength. Now, come to the time scale, that what kind of time scale are there for the these activity strengths or the magnetic variabilities. So the time scale is roughly few seconds to several hours. So this time scale is also varied for this H alpha variation. So it is important to study the H alpha variabilities at shorter time scale. So now come to the observation part. So due to the moderate aperture and the efficiency of the telescope with this instrument, we restrict our samples with the V magnitude greater than 14 magnitude. And this also restrict us to go beyond M6 and M6 dwarfs, because after M6 they are very fainter. So they are very faint. So we choose M0 to M6 dwarfs from these two catalogs, which are first 2018 and Vipin 2011. So we choose the 83 bright M dwarfs and observe during this period, March 2022, April 2021. In the right side panel, you can see the histogram with respect to the spectral type, and the gray color shows our sources, and the red color shows these Lee et al. 2010 sources. So we include their sources also in our analysis to complete the entire spectral range. Now, come to the observational data set. So each M dwarf we have observed with the 1 arcsecond slit width, and in two settings. One setting is the R500 resolution mode, in which we have used which used to determine the atmospheric parameters and the spectral type. And also we monitor for H alpha variability for 1 to 2 hours in our 1000 resolution mode. So this is the picture. We just want to show that how the spectra series look like in the panel A when you club together all the spectrum. And this is the panel A shows the all the spectrum. The panel B shows the light curve of this particular object, and panel C shows the equivalent width light curve. On the axis this is time scale, and y-axis is the equivalent width. So this is equivalent width light curve. And the last panel shows the fractional structure function, which I will not talk about much more, but these three panels I will discuss in the later slides. So first thing with this data, what we have done. So with this R500 resolution mode, we got the spectrum, and then first we have done the spectral synthesis. So with the SGSS template, we find this spectral type to cross-check with that literature data. And then we have also find the temperature and log G value, which are the atmospheric parameter with the synthetic spectrum of VT model. And this is the picture how we have estimated these values. Now come to the equivalent width measurement, that how we measure this equivalent width, and how we have decided that any source is showing H alpha variability or not. So first we have calculated the equivalent width with this simple equation, and we have also include the error. We have also calculated the error equivalent width estimated by the simple error propagation method, and this includes the flux error as well as the wavelength calibration and the continuum fitting error. So in the right side, you can see there I have shown these two plots of the equivalent width light curve. So what we did, we fit a straight line at a constant equivalent width throughout the light curve, and then for the best fit, we have calculated the chi-square value. And once you have this chi-square value, and you have the degree of freedom, which is nothing but the data points -1, then you can check the confidence level of the fitting. So basically this p-value. So once you have the p-value, you can easily say if the p-value is less than 0.05, it means your source is variable. It means that the fitting is very poor. And if the p-value is greater than 0.05, then you can say that the variability is not found in that particular source. So with this exercise, we found that there are H alpha variability found in 53 sources out of 83 sources in that particular time scale. Now, once you have the equivalent width data series, then you need to quantify that how you can say that this source is more variable or the less variable. So for that purpose, we have choose three quantities. One is the delta equivalent width, which is basically the maximum equivalent width minus minimum equivalent width. Another one is RMS equivalent width divided by median equivalent width, and the last one is the maximum equivalent width divided by the minimum equivalent width. So these three quantities show, we plot with respect to the spectral type and find that, okay, the rising trend you can see in these three plots. You can say that the later spectral type shows the higher variability. And one reason could be the age effect. Another reason I will discuss in the next slide. So one thing is the equivalent width, another thing is the activity strength. So to determine what is the activity strength, this activity strength is basically the ratio of H alpha luminosity to the bolometric luminosity. So basically this is a better comparison of activity among the different kind of different masses of the star, and this activity strength we can find with this equation, in which involve this equivalent width of H alpha, and another thing is the chi factor. Basically this chi factor is the F naught by F ball, which is where this F naught is the flux near the H alpha emission and F ball is the bolometric flux. So if you have not the flux calibrated spectra, then you have to find this chi factor by another methods. So one method is that you can use this color I minus j of that particular star, and you can find the chi factor. So once you have this LHL available, then you have the statistics with respect to the spectral type. So on the y-axis, I have plotted this log LHL available with respect to the spectral type. And one thing we can directly see in this plot that the later spectral type have the lower activity. But in the previous slide, you have seen that the later spectral type shows the higher variability. It means, so here's the reason that why they are more variable in the later spectral type, because there's a reason that because when you talk about the lower activity, so there is a if there is any small change in the H alpha emission, so it can be more prominent for the low active star. So that's why we see the more variability in the later spectral type. Now, if we want to connect these variability with the rotation period, so first you have to find the rotation period. So we have used this TAS and capital K2 light curves to find the rotation period, and we use the periodogram technique to use which is presented in this light curve package. So this picture shows a phase folded light curve for this particular object, and the right plot shows the periodogram of this particular object. So this rotational period we have also checked with the variability parameters which I have showed earlier, and we find that the lower rotation, which have the lower rotational period, they are the more variable, and the later spectral type. Now come to the next thing, which is the star spot filling factor. So basically, this star spot filling factor nothing but is the total area of the spot which are present on the stellar surface, and then with respect to the total area. And we can find this star spot filling factor with this equation, in which delta F and F values clearly mentioned, clearly can understand by this figure, and T spot the star spot temperature, and T star is the effective temperature. So with the help of this, we find the star spot filling factor for all the stars, and here is again we plotted these three variability parameters with respect to the filling factors. Now for the summary, we have found that there are 83 M Dwarfs, and we observe them within this period, and also we have found the 53 sources are variable out of the 83 sources, and H alpha variability increase with the later spectra as we go for the early to later spectral type, and the activity strength is roughly constant between M0 to M5, and later it is decreasing for the later spectral type. And also we have seen that the derived rotational period is roughly between 0.2 to 10 days, and if your rotational period is less than 2 days, then the variability is higher. And also the smaller filling factor sources showing the more variable across the spectral range. So this work already have been submitted to MNRS, and it is under revision. And for the future purposes, we are designing an intermediate resolution spectropolarimeter, because we know there's still lacking a consistent picture to link the magnetic fields and the dynamic mechanism, rotation and activity. So we are working on this intermediate resolution spectropolarimeter designing. So please, you can visit our poster on the designing of this particular instrument, M-Force EP, which is going to mount on the 2.5 meter telescope. So thank you.
Thank you. Very interesting talk. Excellent. And we have time for a couple of questions. I think in the interest of time, I think we will wind up. And I thank all our speakers. I thank again for very, very exciting talks we had in this session. And the next session will start in another 10 minutes. So we have a break for 10 minutes. And the GBM starts, there is some change in time. The GBM now is at 6 p.m. Thank you. Thank you very much. Yes. The next session will again resume at 4:30 right in this room.
I'll run 10 बार करना है. Yes. ये लोकेश जो अगला है How are you? Yeah, thank you. I got my data.